So I was just talking about anthropogenic greenhouse gas sources. And I just said that fossil fuels probably the biggest. Agriculture is another one. Over irrigated fields will produce methane because you get these anoxic conditions, and will also produce nitrous oxide as well. Fertilizers and things, manures, these things have nitrates in them, and that will add to the nitrogen cycle and will produce nitrous oxide as part of the nitrogen cycle. And livestock is a huge contributor of methane, as cows are digesting their cellulosic food in their gut. They're basically being fermented by the microbes in their gut, and that produces lots of methane. The manure and things that they produce also produce carbon dioxide as they decompose, as well as methane as well. Another very important contributor of maybe not so much greenhouse gas is deforestation. As we deforest, as we cut down our trees, we might burn them, or we might just leave it to decompose, and that's going to add more carbon dioxide. Also, because we're taking away the trees, they're not doing photosynthesis anymore, so we're taking away their photosynthetic capacity. So if you're going to have you're going to have increase in the respiration and decomposition and decrease in photosynthesis, so that's going to be overall increase in CO2. Landfills also produce methane, as we talked about when we were talking about waste management, right? They're also industrial production as well. We actually produce some of these greenhouse gases directly. So, for example, CFCs, the compound we talked about that damages our ozone, is also a greenhouse gas. It's a very potent greenhouse gas. So remember, I said that, don't mix up global warming with the ozone depletion, because these are two separate topics and they're two separate things. And once you get them mixed up, then you are not understanding the mechanism behind them. Well, one commonality between the ozone depletion and climate change is a CFC is a key player in both. CFC destroys ozone, and at the same time, it's also a potent greenhouse gas. But the good thing is the CFC is declining, because it's probably one of the only things that's declining of all the greenhouse gases, because we put a stop to producing that. Also, just a note, ozone itself is a greenhouse gas. So not only is it a pollutant in the troposphere, when we breathe it in, it's bad for us, and it's it is beneficial in the stratosphere, but the most of the damage is happening in the troposphere, where it's also a respiratory irritant, but also a greenhouse gas as well. Okay, so so here are the anthropogenic sources of greenhouse gases. This is looking at methane here and looking at where most of it is coming from. A lot of it is coming from livestock. A lot of it also is coming from landfills and just leaking from natural gas and petroleum production and mining. Okay, so that's methane. This is nitrous oxide. A lot of it is coming from the soils, especially these agricultural soils, as part of the nitrogen cycle. And then you have that carbon dioxide. By far, it's the fossil fuels used for energy and for transportation. Okay. IPCC is the Intergovernmental Panel on Climate Change. So this was, I guess, established in the 1980s. Every few years, they publish a report on what the status is and what we know about the science of climate change. And every time it comes up with it, it's kind of depressing. But there are thousands of scientists who are kind of looking into this, and I guess some of them are involved in the research themselves, but what they're doing is they're looking at all the studies that has come out and doing these, fancy meta-analysis and things like that of how, what basically all these studies are saying and how reliable some of these studies are. And they present their conclusions, and they also give suggestions of what needs to be done in terms of policies and things like that. Okay. And so let's look at what some of the things that they are finding. All right, so this is the data behind changes in carbon dioxide and global temperature change. You need to know this guy's name, or at least you need to know this graph. Charles David Keeling is the kind of the founder or the producer, or the Keeling curve. The Keeling curve is this very famous curve now, or this graph now, that shows carbon dioxide in the long term. I guess before that, and this started back in the 1960s, so he started this measurements back in the 60s. Before then, people looked at carbon dioxide, but they didn't really look at the long-term effects, so they didn't really see the patterns. They saw that it kind of sometimes was high, sometimes was low, kind of fluctuated, and they weren't really looking at the big picture. He's the first one who did a really long-term study of CO2 in the atmosphere. And he did it from an observatory in middle of the Pacific Ocean in Hawaii, and charted his findings. And his students continues to monitor this data. So this observatory you can go to the website and you can find out what the carbon dioxide level is right now, and then what it has been for the past week and past month and past decade and whatever. You can see all the data. It's all available online, right? And you can see two observations based on this graph. One is that there's a zigzag, right? So this zigzagging happening is very, very regular. It's happening, seasonally. And so basically, this is a seasonal fluctuation in carbon dioxide. Amount of carbon dioxide changes because of, the amount of photosynthesis varies seasonally, right? So in the spring and in the summertime, the carbon dioxide level goes down because there's increase in photosynthetic activity. A lot of the photosynthesis that affects this is coming from land plants, and most of the land plants is in the northern hemisphere where there are plants. I mean, the southern hemisphere is mostly ocean. So the fluctuation that we're seeing is based on land plants in the northern hemisphere. So that means spring and summer in the northern hemisphere is when the carbon dioxide drops. And then in the winter, as the photosynthesis slows down, and then you have more respiration than photosynthesis, that's when the carbon dioxide level goes up. So you can kind of see how natural processes like photosynthesis has measurable impact on CO2 in our atmosphere, right? That you can actually see this fluctuation that's happening seasonally. But what's also undeniable is this increase that's happening over time, and that is, that is what we're concerned about, the fact that we are seeing this very regular increase in CO2. We are well over the 400 parts per million mark now, and that is due to anthropogenic impacts. So what's causing this increase in CO2? Or where is it coming from? Well, we can look at, so if you look at this graph here, it's looking at CO2 emissions by country. So who's producing most of the carbon dioxide? Well, it's China and the United States, right, by far compared to all the other countries. These are the two biggest emitters of CO2. Just keep in mind, however, China is, produces more than U.S. But if you look at it per capita, remember China has a lot more people than U.S. Then China's way down here. So this is per capita emissions of CO2. And so when you look at it per person, then United States is at the top of, both of these graphs. Australia's up there, but remember Australia is tiny in terms of population. So overall, it doesn't have much of an effect. Same thing with Canada and Saudi Arabia. They're down here somewhere as well in terms of overall emissions, even though per capita is high. So you got to look at both when you look at these things. But that's where the carbon dioxide is coming from that's causing this increase, right? So we know the CO2 is a greenhouse gas, and the CO2 is increasing. Well, is that having an impact on the temperature? Yes. We are seeing overall 0.8 degrees centigrade increase in temperature between 1880 and 2009, this seems like a teeny tiny little bit of, this is less than a degree, right? But the amount really varies across the globe. In some areas, we're seeing very little change. In some areas, we're seeing a lot more change. So this is all, this is just an average for the entire globe. Okay, and this graph is showing the changes over time. So you can definitely see that a lot of the temperature change is happening within the last 100 years or so. So what we need to now look at is, okay, so the CO2 is increasing, the temperatures looks like it's also increasing as well. Is this consistent with what might have happened historically? So scientists have looked into historical measurements of CO2 and temperature in the past. And how do they do that? Well, they can look at things like fossils. So they look at these fossilized remains of these microbes, photosynthetic microbes called foraminiferas, or call them forams. These forams are temperature specific. So I guess different species or different forms of forams are more abundant in different temperatures. So by looking at like core samples of bottoms of lakes and oceans where these things exist, I guess oceans, I think they're mainly oceans. You can find layers of these things in these core samples and go back many thousands of years of what the temperature profile was like back then by looking at the types of foraminiferas that existed. You can also look at ice core samples, right? So that you drill ice cores, because some of these ice have been around for thousands of years. The further down you go, the older the ice, and there are little air bubbles that are trapped in them as the ice formed, and you can take measurements of them. You can look at how much carbon dioxide was there in the ice, and then you can also look at things like oxygen isotopes to determine what the temperature was like at that time. So when you take all that information, you can put together a timeline of what the CO2 level was like going back hundreds of thousands of years. Okay, we can't go back millions of years, but we can go back, at least about 1 million years or so, I think. And this is what we see. This is CO2 levels going back, to 400,000 years ago. And you can see that it fluctuated, right? There's some times when it was high and there's sometimes it was low, but this is where we are now. So what we're seeing right now is unprecedented, at least within the last million years, right? So that's alarming, right? And this is not just for carbon dioxide. When we look at data for other greenhouse gases, we see a very similar trend. So this is for carbon dioxide. We can see that it's, this is within the last 10,000 years, right? You can see huge increase in carbon dioxide within the last, century or so. Same thing for nitrous oxide and methane, right? So these are all greenhouse gases that contribute to, that could potentially contribute to climate change, and we see huge increases, unprecedented increases in all of these. We can also, when we combine this data with the temperature data, this is what we see, right? So the purple is the CO2, and then the blue is the temperature, and we can see that they almost overlap almost perfectly, right? So whenever you have high CO2, you also have high temperature. When we have low CO2, we have low temperature. So you can find two things from this graph. One is that it's very cyclical. There's regular changes that happen. So Earth has gone through these cycles of changes, right? And scientists attribute this to the orbit and the tilt of the Earth. That also goes through kind of this cyclical change that affects our climate. So we need to take that into account. And another thing that's very, very obvious is that CO2 and carbon carbon dioxide and temperature is very tightly correlated. You know, one seems to be related to the other. Now, this doesn't show causation, right? Just because you see one and then the other, that doesn't mean one causes the other, but there's definitely a correlation. But from this, you really can't tell, is carbon dioxide causing the increase in temperature, or could it be also when there's increasing temperature, you know, the level of carbon dioxide increases, and there's other, you know, plenty of mechanisms that could account for that, right? But you know, either one is a possibility, because, you know, at least the science says that you know, you can have either one or the other. Okay. This one is showing the short-term temperature trend. So this is within the last 2,000 years, right? So again, within the last century or so, we see a much rapid increase in temperature increase compared to what's been going on for the past several hundred years.